We are going to talk about these word problems because it kind of got thrown in here. There's some matrix ones at the beginning, and then there's some vector stuff. I want to talk about matrix ones first. We're going to actually do number one. This is number one off that problem, off that sheet. So if you want to write it down with me, that would be good, or check your answers on it. But what we're trying to do is kind of see some of the applications for where matrices get used on a smaller note. So this says Carmen Fox owns 3 fruit farms, which she grows apples, peaches, and apricots. She sells the apples for $22 a case, peaches for $25 per case, and apricots for $18. First part is write an inventory matrix for the number of cases of each type of fruit from each farm. So they give us this big table right here, all this information. So farm 1 has 290 cases of apples, 165 cases of peaches and apricots. So we want to turn this into a matrix. What size matrix will we need? How many farms do we have? There's 3 farms, right? How many products do they have? 3 products. So it's going to be a 3 by 3 matrix. And for this setup, we'll have to double check it, but we're going to put it in exactly like it looks right here. 290, 165, 210, 175, and just before we move on, if we were to present information in this, right, and I were to ask you in this matrix, let's call this matrix I, since it's the inventory matrix, okay? What does I 3, 2 mean? So now we're dealing with elements and we're looking back at meaning from that matrix and that element. So let's find that spot first. And this isn't part of this question directly, but I do want to look at it. So remember, this is 3rd row, 2nd column. So from the top, 1, 2, 3 over. So the number we're looking at is this 75. What is the meaning of that 75? It means that farm 3 has 75 cases of peaches. So when we do this and we use matrices and tables, almost essentially the same thing. But what we're stripping away when we deal with the matrice is we're stripping away a lot of the information that's on the outside so that we can use matrix operations to take that information and find results from it, okay? So just remember, it still has the same values and same information inside of it. We're just making it look a little different, but we got to kind of remember what it is. So when we do this operation at the end, we can kind of get an idea of what we're finding. So this matrix I is part A. Now it says write a cost matrix for the price per case of each type of fruit. It gives us a hint and it says write a column matrix. Which ways are columns? They're up and down. So there's a reason we're going to use a column matrix here, and we'll see it when we get to C. So we're going to use a column matrix this way. And what are our costs? So let's see, let's put them in the right order. Apples were $22 if we wanted to buy them. Peaches were $25. And apricots are $18. So this is our price per case matrix. So we looked at, let's call this one P. What does P12 stand for? Well, P12, I'm sorry, I did that completely wrong. 2, 1. 2, 1, because there's only one column. That's at 25. That means that our peaches cost $25 per case. Now, the reason they wanted us to use a column matrix here is we want to use matrix multiplication to find the income from each one of these fruit stands, right? If they were to sell all these products. Let's talk about this without the matrix. If we wanted to figure out how much money that we would make selling all of the product in farm stand 1, what would we multiply the apples by? How much are they worth per case?
22.
These are worth $22, right? Peaches are worth 25. Apricots are worth 18. And then we would repeat that process again and again for each one of the stands Then we'd have to do what with them? We would have to go and add them all together to find out how much. What if we set this up with matrices? The matrix is actually going to do, think matrix multiplication. It tells us to take stuff in the same positions, multiply them, and then add them all together to get our answer. That's exactly the operation that we want to accomplish here, which is why this comes in handy. So what this is saying is take your product matrix, or your inventory matrix, I'm sorry, that's what we called it. And we want to multiply this thing by the cost. And remember the way that our multiplication works, we're going to take rows times column, right? And that actually the way that we have this set up, because we set it up to make this happen, 290 times 22, that's what we wanted up here in the first place. 165 times 25, that's what we wanted to have happen. 210 times 18, that's what we wanted to have happen. And then as we move down and we find each new entry in our resulting matrix, how big is the resulting matrix going to be? Well, let's look at our stuff. This is a 3 by 3. This is a 3 by 1. So we can multiply those because these two match. The leftover stuff tells us how big our answer matrix will be. It's going to be 3 by 1, meaning our answer, which would make sense, we're going to get the total amount for farm stand 1, 2, and 3 once we add them all together here. Now for something like this, we say, well, why would I just multiply this and I'm going to have to add all these things up anyways and do it by hand? What does it save me not to just do this by hand if I have to do it by hand anyways, right? Well, that's where, when we set these up, matrices we use a lot in computers, but even more, we have, if I can find it, we have a matrix calculator. So take a computer and go to the matrix, type in Desmos matrix and search for it. It'll be right on the top. And when you click on it, it's going to bring up this calculator right here. And our graphing calculators, if you have one on your desk, you have one at home, you can also enter matrices in there and it'll do the operations for you quicker, which is why we do these things in matrices. But you can click new matrix because we want to do the addition, we want to do the multiplication. So I have it written down on paper, but we know that matrix, our first matrix was 3 by 3. So let's set that up, 3 by 3. And the first entry was 290. We had 165. You can use the arrow key to go to new stuff. And that one was our inventory, right? So I'm going to enter the inventory in there, and I'm going to hit enter. Now it knows what matrix A is. I'm going to click new matrix again, and now I'm going to set this for our cost matrix, or how much each case was worth. And that was a 3 by 1. It was 22. Oops. 25 and 18. If I enter the matrices into the calculator, what do I want to do? I want to do A times B, right? So we can actually click these buttons. A times B. Notice what we see right here. It actually does all the dot product stuff for us, where it takes the row and the column and multiplies them all together and adds them. And it finds our answer. So our answer here is this. And I'm going to cheat because I'm going to screen clip it right in here for our answer. So by using a matrix and using something that will actually add these things for us, and multiply everything else, because it'll do addition, subtraction, and all the long operations. But multiplication is the one that I think this saves us a lot of trouble with, okay? I wanted you to know how to do it, But what we're doing is a problem like this. Now I want you to think, this inventory is really small. Say we had 10 products at 10 different stands. Then the multiplying and adding would become extraordinarily tedious. But if you set it up correctly, we can easily use matrices and the power of our technology to make these things come out much quicker. Okay? So let's talk about what this answer means. So we did the matrix multiplication on our calculator. So this one right here, let's call this one our profit matrix. So this one is P because it's profit. Nope, we already used P. We use that for this. I don't know, let's call this one A just because we need something. What does A 2-1 mean? So let's find that value in this matrix A that we just found. A21 is this number right here. What does it mean? It's $13,270. Now let's look at the multiplication. What are we trying to find? Total income from all three of the fruit stands if they sold all their product, which makes sense. We talked about the operation that we did. So how much money is that? That's $13,270. Which fruit stand? Fruit stand, farm stand 1, farm 2, or farm 3? This is farm 2 because it's in the middle. Remember, 2 was right here when we set this up. So that's its multiplication. Farm stand 1 is the top, 3 is the bottom. So this one is 13,000. This is the profit. From stand 2. Profit from stand 1 is the top number. How do you find the total income from all three of them combined? Just gotta add those up. And so I got, when I added them up, $31,850, which I hope is right. What we use matrices for is when we see a repeated calculation that we're going to do over and over, we can set it up in a matrix, especially use a matrix calculator to help us do those operations more quickly and more efficiently and a whole lot less paper. The other, I think there's only 3 on there. Most of them are pretty similar, but you got to make sure you really read through and set them up, okay? And always check, because you'll be leading towards some sort of multiplication or addition, that your matrices are right so you can add or subtract. Let's jump over and talk about the vector word problems, okay? The first part of it wasn't really word problems. It had a definition about how to find magnitude, which is what we just did. But this is the important part of this one, is it tells us how to find the direction. Okay? So what we're going to do is we're actually going to find the magnitude and the direction of each one of these vectors and write this out. Direction is going to be an angle, which means that's why we're using tangent for it. We're actually solving for that angle in the right triangle that's made. So let's draw each one of these vectors first. So vector B is -5, +2. So that means its endpoint is going to go out here. So when we go to find its magnitude, what we're actually going to find is we're going to find the length of the line, okay? Length of the green line, and then the angle we're going to find is actually going to be this angle right here. From where positive x is all the way over to where the green line is. And when we get into the trig unit and everything else, that's actually the standard way that we measure angles in the coordinate plane. And just have to trust me on that one until we get further definition for that, okay? So we're going to follow the same thing. This is exactly what we just did with magnitude before. But we've got 2 points here. We start this thing at 0, 0, and it goes out here to -5, 2. So when we find the magnitude of B, this is going to be, we can follow their formula up here. It's going to be the square root of the difference of our x's. So that's going to be -5 minus 0 squared. And then we're going to go 2 minus 0 squared. So we get the square root of 5 squared plus 4 squared. So 5 squared is 25, 4 squared is 16. So 25 and 16, I'm sorry, I went 4. That's not 4, you guys got to stop me. That's 2 squared. I did the answer instead of actually doing the math. 25 and 4 is the square root of 29. There's no perfect square, so this is the magnitude of that thing. And when we go and we find the direction, that's going to take us a little bit of reasoning through. So we're going to use tangent. Let me delete our highlight here so we can see this. Now what they did here, they're doing an example from this one right here. We have an x of 3 and a y of 5. Tangent is always going to be the y value over the x value. That's what tangent is equal to. Okay? So our y is 2, our x is -5. So to set ours up, we're going to go tangent of whatever theta angle, and the theta we're going to find is right here. It's going to be 2 over -5. Now, what it says, it doesn't give you a lot of information here, but we got to remember when we're solving for an angle, we use inverse of that function, which is really a button on our calculator. So to move this over, it gains this little -1 sign. And really what that's going to do is it tells the calculator, I want to know the angle from these two sides. And we can plug this straight into the calculator like this, and it's going to give us an answer. So let's flip back to our calculator and plug this in and see what it says. So we are going to click So we got to get out of the matrix one. We're going to go to the scientific one, because it's got the functions that I need by clicking right here. So we wanted to find the answer to inverse tangent of 2 divided by -5. So inverse tangent is in here when you click functions, and it's that tangent with the little -1 sign, and it gives you a set of parentheses. So we wanted 2 divided by -5. You see the answers show up over here. It tells us our angle is -21.8. So let's go with that for right now. So it tells me that this is -21.8. What in the world's a negative angle? That's weird, right? With this, when you get something weird like this, what it's telling me, positive turns this direction. Negative turns clockwise. So what it's telling me is that it's drawing a line this way, and that this part of it over here is 21.8 degrees. These are going to be tough, and we're going to have to take them one step at a time until we get to the trig stuff and really understand what's going on. But it's not telling me this angle. It's actually telling me this one inside is 21.8. But that's not the way that we would represent that. So let's make this bigger so we can see this. Here's our line to our point, and we figured out that this angle right here was 21.8 degrees. But the one that I want for my answer is that one. Anybody tell me how to find that one? What? 180 minus 21.8. Was it 21.8? Okay, because we always want the angle from the positive x-axis to our line in a counterclockwise direction. Okay, so that's what 158.2. So that means our angle is actually 158.2 degrees. So this theta isn't this. Ours is 158.2 degrees. It's going to be positive. Because another way to write this vector B is by its magnitude, which is the square root of 29, and its angle, because that is a magnitude, its distance, and then its angle tells us which direction it's pointing in. We would do the same thing here for C. Let's do that one on another slide. So C was 2, 1, negative 2, 1. And these are the X and Y components. So it's a point, and it's out here at negative 2, 1. So we're going to end up with the same type of thing for the angle. We're going to have to subtract to find it in that quadrant. But we can easily find its magnitude following our formula. Remember, it's what we're doing is with X and Y in component form, pins it down at 0, 0. So when we find its magnitude, we're going to use our square root of the difference of the X's, difference of the Y's. So we're going to go negative 2 minus 0 squared and 1 minus 0 squared. So that is going to give us negative 2 squared plus 1 squared, which is 4 plus 1. So its magnitude, its length, is square root of 5. We're still going to use tangent. We'll always use tangent to find the angle. And this fraction is what's going to change. It's always going to be the y value over the x value. So this is going to be 1 over negative 2. And that is what we will plug into the calculator. Figure out about what it gives us as an answer. So let's jump back over here. And since we have it kind of typed in, we can just change here. So it was negative 2 on the bottom and 1 on the top, right? And it tells us negative 26.6. So that means it tells us negative 26.6, but remember, that's the negative this way or the positive right here. So it tells us this angle. But that's not what we want. So we've got to go 180 minus 26.6. So that is 153.4, right? Awesome. So this isn't what we want. This means that its angle matches up like that. So another way to write vector C, its magnitude, square root of 5, and its angle. And the way that you get tipped off that a vector is being written as magnitude and angle is that your second thing is it's going to have a degree symbol with it. So you know, okay, this is the length of the line and its angle, and you can at least sketch those out. You shouldn't start with many of those, but just another representation of it. A little bit more sense? All right, I do want to do a couple of the actual word problems there. I think I've got number 7 and number 8 on here, just to kind of get you in the right direction of what I was asking for you to think about here, because these are a little bit different. So this says the vector V represents the speed and the direction the wind is blowing. So does it give us an actual length or anything? No. So let's just draw a vector. And let's call that vector, that's vector V. That's how strong the wind is blowing and in the direction it's blowing. Suddenly the wind picks up and doubles its speed, but its direction does not change. So before we write an expression for this, in comparison to the green vector I've drawn, what's going to change about it? Does its direction change? What changes? Its magnitude, right? Because now the wind is pushing against us twice as hard. So when we look at this and we think about this problem, the direction didn't change, but the speed is increased, right? How much? Double, right? And I'm going to try to make this as exact as possible. So that's why I'm doing this way. It should be, it's pretty close, twice the length. How would you say that mathematically? It's not just V, but it's, we added them, didn't we? It was really, I can put the other one back now. It was really V and another V. Right? It was now two of them. So when we look at this, it's like we're adding these things together. I didn't get them quite close enough. They're not quite perfectly straight, but I think you guys are getting the idea. There, that matches a little bit better. V plus V is how many V's? It's two V's. So when the wind doubles, if we look at an actual expression for it, well, the expression would be either, well, that's like V plus V, which would be 2 vector V's. It would be like multiplying the component. So if I did give you a component and it said, hey, it doubled, say we knew that the vector V had X and Y components of 3 and 6. If we doubled that speed, well, that means we would need to find 2V, and we could actually double those components and see that that vector doubled up before. All right, this one's a little tough. Jana is swimming in a triathlon event. The ocean monitor is still. Her velocity can be represented by the vector 2, 1. Let's actually draw that. And I'm going to try my best to make this exact so when I explain it, you can see it. So Jan's vector for how she's swimming is 2, 1. So she's going like that, right? And so she's out in the ocean. During the competition, there's a fierce current represented by -1, 1. So let's actually draw the current vector. And I didn't get my line where I should have to make these exact, but it's pretty close. Pretend that those are even. So she's the blue vector. Now the force is, what we're asking is, what represents her actual vector, how far she's swimming in that time? Is she still making 2, 1 miles per hour? Anybody ever swam against the current? Ever go to the beach and they tell you not to swim against the riptide that's pushing you this way? You just tire yourself out? Because the water pushes you out, you've got to swim against it, so it takes that much force for you to even make any progress forward. So this vector, even though it's listed here, let's make copies of these things. They shouldn't be on the ends of each other, right? This vector, if we wanted to put it together with hers, really needs to go right on the end of where hers is, and it's pushing her backwards. Meaning that instead of making it all the way to the end of the blue arrow, you've got to take away that space that she has here, where she ends up. So if we take that away and we think, well, this X component is 1 and this one's 1, so that means from here, when we put that red vector onto here, we've got to move it up here and have it push back. Now we know that she was here at I'm sorry, that vector's not right. It should be like that. I'm sorry. Because it's not just, it's pushing her like this. I apologize. Right? Because it goes down one and over one. It's kind of like the vector voyage thing. She's trying to get to right here, but the ocean current pushes her back, and she actually only gets to right here. So her real vector is the addition of these two things, which is just 1, 0. Her resulting vector is really just 1, 0. Now, I did that graphically. I could actually do that algebraically. If Jan's vector is 2, 1, and the current is -1, -1, I can, to figure out what the result would be, I can add those two things together. So we would end up with 2, 1 plus -1, -1, which means the resulting vector, the distance, the way that she actually traveled, 2 plus a -1 is 1. 1 minus 1 is 0. Could also represent it that way. I'm trying to tie the two things together because I think it makes vectors make a little bit more sense, guys.